Welcome to this interactive session on using the Calliope Energy System Modeling Framework. I'm Bryn, I'm one of the lead developers of the software, along with Stefan, who's here, and other contributing developers are Francesco and Tim, who are also in the call and will be helping us also to field questions when you get to actually applying stuff in the modeling framework yourselves. The purpose of today is really an intro into the modeling framework and building a model yourself that can be used to look at energy system configurations for, say, a decarbonized society, decarbonized Europe, decarbonized individual country, depending on what you're interested in. The sort of high level objective is to learn the basics of high resolution energy system modeling, to explore planning and policy decisions. This is sort of, I guess, in a way generic to all sorts of energy system models, and we don't try to say that, you know, the result of what you get is any different to what other energy modeling groups would get. But with Calliope, the process of building a model, we believe, is a lot more straightforward and has a much lower barrier to entry, which hopefully you will experience today. The key sort of four sub-objectives to that are about interpreting the inputs and results of a Calliope model, and we'll have a brief look at that. You should be able to create a Calliope model based on a set of data describing energy supply technologies and demand sources. You'll have a chance to give that a go. You should be able to compare different model outputs. We'll play around with that. It's going to need a small amount of Python programming to do that, but there are some examples already online for you to make use of. And also, you should be able to, at the end of this, identify where to look for help when you're constructing new or modifying an existing Calliope model. When you want to do more than what our session is going to allow you to do, you're going to need to be able to look at all of the resources we provide to be able to move forward, and we hope that we provide enough for you to be able to do that. So what is a Calliope model? For us, it's a set of building blocks that are used to describe an energy system. And imagine that you've got an energy system that is, say, the UK, and within that you have some electricity demand, or demand for anything really. But let's say electricity. To meet that demand, we know we're going to need to have some form of electricity supply. And to build up that supply portfolio, particularly in a decarbonized society, we're going to need, say, a mix of renewables, PV, wind, hydro, maybe things like firm capacities related to biofuels, maybe nuclear. But a range of technologies are available that could provide the supply to meet demand. On top of that, we know that these renewables are variable in time, so we might need to rely on some degree of storage. And furthermore, we might also want to rely on our neighbors to import and export electricity. But when you've got all of these technologies available to you, it might be difficult to know, you know, how do we invest in these different technologies to meet demand? Because there's lots of ways of doing it. Some examples that, you know, if I created sort of just a mental model of demand and thought, you know, how could I meet that demand with supplying from different technologies? I could say, okay, I don't want any oversupply at any point. I could think, okay, I'm going to have a certain amount of wind based on the profile for wind, a certain amount of PV invested, and that's going to produce a certain amount in the middle of the day. A small amount of hydro, and at this point, I've invested in all my technologies and I'm ensuring no oversupply. The rest, I can see a gap. I will rely on imports from neighbors. That's just a simple mental model, could be a possibility. We could look at the opposite and say, okay, no undersupply. We're going to ensure that there's enough supply from our domestic technologies to always meet demand, no matter what. That means that we've got a lot of oversupply that we're going to have to export. And so we've got a much larger total capacity of technologies between one and the other situation, but they both lead to the same end result, that supply meets demand. We could bring in storage and have a completely different setup, but maybe there is also some optimal combination of these technologies that ensures that demand is met by supply, but it's done in a way that is at the lowest possible cost. So that means that the total investment in technologies and the cost of running those technologies is at the lowest possible value. And we think of this, this least cost as being sort of a least cost to society, because within our energy modeling, it's not really possible to attribute those costs to individual bodies or even to model the markets. Market models are sort of a different entity entirely. So rather we get sort of a society-wide cost, and we can compare that between models to say, is the overall cost of system A more or less than system B, where A and B are two different scenarios for how we might reach a decarbonized society. When we have these problems and we want to start them, as I say, we've got demand, we've got supply, we've got storage, we've got transmission. And this is how we break up the explanation of the model within Calliope as components of the model. So we have technologies, and those are things that produce energy, consume energy, convert energy, store it or transmit it between different locations. And so we need locations. And in each of these locations, usually they describe a geographic context. You could go abstract, but the model doesn't require you to be definitely in the real world. But within each of those locations, there needs to be a set of available technologies to meet demand at those locations, as well as the ability to link between each of those locations and other locations. I showed an example yesterday which had Iceland in the European network, and without a link to the rest of Europe, Iceland can go on and do its own thing, but you can also link Iceland to the rest of Europe, and so share in the production and consumption of energy between islands and the mainland. Once you've got those components, you need to sort of wrap them in a range of things to ensure that the Calliope modeling framework understands what's going on. So you have top level configuration options that say which are the files you want to bring in and you care about, which are the, what's the Calliope version you're using, the name of the model, things like that. You also have overrides and scenarios, which are ways to describe different situations for your technologies, locations, or links, different costs, different available technologies, different demands. And you also have the ability, and this is a relatively new addition, but one that we probably won't go into in detail today, you can read in the documentation, the ability to provide system-wide constraints where you can say, okay, the total CO2 emissions across the entire system cannot go higher than a certain amount. And putting all of this together, you end up with a Calliope model that you can run and optimize for, say, least cost. But you could also look at something like least CO2 emissions or a variety of other things. So when we have these building blocks and we want to describe a system using them, we might start by thinking about the regions that we have in our model. In this instance, we have region 1 and we have region 2. And within those, we would probably say we have some kind of demand for electricity. We could have demand for literally anything, and usually that demand follows some kind of time series that we've stored in a CSV file. We then say, okay, what are the technologies that could be available inside this region? We're not predefining that they have to have capacity above 0, that they have to be deployed, but we want to say that they are available. The model needs to know that they are available in that region. So we say, okay, in this instance, we've got concentrating solar power. We've got some land in this region that could have concentrating solar power on it in both regions. And we want to know how much of that land to use for concentrating solar power to meet electricity demand. In one region, somebody has also given us the ability to use a building to put loads of batteries in, and we don't know whether we want to use it or not. So we've got the ability to use battery storage in one region, and we don't know how much we should make use of that, how much we should invest in that. Somebody also mentions the possibility of using a combined cycle gas turbine, and we're not sure what the impact of including that will be. And we want to consider a scenario where combined cycle gas turbines may be in the system and see the result of including them. And then ultimately, these two regions can be connected together. So what's going on in one region can be connected to what's going on in another. And so you could send oversupply to an undersupplied region if needs be, but you have to invest in that transmission link. So there is also the need to spend money on reinforcing that line, and you're not sure how much you want to do that. All of these are model components, and then you ultimately wrap it in the model and run configuration, and with any model-wide constraints if you wanted to. I'm going to briefly show you what that looks like inside when implemented as a Calliope model, and hopefully show you how it is a really quite simple representation that you can work with yourselves. So here you'll be able to see a file structure which has got 4 files in it. These 4 files define that model that I've just described to you. So we have a YAML file, and YAML is what they call, and we like to also call, a human readable text that describes our model and can describe all 4 forms of configurations. And then we have 3 CSV files, and this describes our time series data. If we go into our model YAML, we can see a variety of configuration options and numbers. But what I want to draw your attention to first is what's at the first level. You can think of this as a hierarchical structure. So things further to the left are higher up in the hierarchy.
You zoomed, good, thanks.
No problem. So to begin with, we've got these high-level configuration options, as I said, what was green in the description, where we say what is the name of our model, what Calliope version are we using, where can we find the time series data, and what period of time are we considering here, just 5 days. We then have our technologies. So we say, okay, we've got our technologies, we've got our concentrating solar power, that's 1 level down in the hierarchy. And then we've got a variety of information associated with that technology. We've got its name, we've got what kind of technology it is, and we'll go into more detail about this in a moment. When we're plotting, it's nice to have nice colors, so we've got a color for it. And we've got what is the energy out. And in this instance, it's called power, but you could call it electricity, you could call it heat, you could call it whatever. Provided you are consistent within your own model, it doesn't matter what you call things. We then have constraints, and those are the important things in our system, such as what is the maximum amount of storage you can have in your concentrating solar power plant? What is the time series of your solar power productivity entering into your concentrating solar power plant? What is the efficiency? And what is the maximum discharge of power that you could have from your concentrating solar power? And then, given that we're going to be looking at the least cost, we also care about costs. And you can put in a variety of costs into your model. And here we're talking about monetary costs, but we could equally say, okay, there's a CO2 cost to it. And every time we are producing energy, we also need to pay a certain amount of CO2 cost. And maybe we say this is tons of CO2. And that would allow us to track CO2 costs and also put a cap on it, or even minimize CO2 costs in our system rather than monetary costs. We then have our battery storage. Again, it's the same structure as the CSP, but with just different information stored in it. So it's a storage technology, and then Calliope will know how to handle that. And then certain key information associated with storage technologies is given. Demand is also considered sort of part of the technology building blocks. It's just a technology that consumes within our system rather than produces. It doesn't need much information provided to it because this is the kind of information we're going to give on a location by location basis. Demand is going to be different in region 1 compared to region 2. We have transmission. Parent is transmission. So we're really making use of these building blocks of Calliope to describe our system. And then we have our locations and we give it coordinates. Geographic coordinates might be the center point of a country, but could also be sort of in Cartesian XY coordinates if we wanted to. We then have the technologies we want to define. And in this instance, we can also define location-specific constraints. So these constraints beforehand are just generic to the technology, but in a specific location, we might want to provide an override to that. So in this instance, region 1 has got a particular discharge maximum of CSP that is different to the default. But the structure of how we define it is the same. It's still the technology name, constraints, energy cap max, exactly as we did in technologies. And we provide 2 different CSV files that point to different demands for region 1 and region 2. If we have nothing to define for a technology in terms of its overrides relative to the default, we just define its name and nothing more. And that means that in region 2, there will be CSP and batteries. But in region 1, there won't be any batteries as a possibility because we haven't defined it in that location. We then link region 1 and region 2 with a comma in between, and then provide, again, the technology that's going to be in that link. And we could provide multiple technologies if we have them. And again, a link-specific capacity here that says along this link, this is the limit. And then finally, we've got overrides, which ultimately you just take your configuration, you indent it a few times, and you put it under the name of an override. Otherwise, the structure is exactly the same. So you have your text, you have a new technology in this instance, a combined cycle gas turbine. The information is all the same as you would do just for a standard technology, just indented a few times under the name add CCGT. And this also override provides, gives the CCGT to the location of interest. We can have another override, and that can have a different, say, capacity for a technology, and then we can have those 2 overrides linked together into what we call a scenario. So scenarios are groups of overrides. If we then look at what that means for when we load it in, we're going to just show this to you now in a quick way, and then when you work on it yourselves, you're going to get the chance to look at it in more detail. So we import Calliope, we can run a model that has now optimized this situation, and we can have a look at what the overall capacities are of this optimized solution. So we've got a certain amount of concentrating solar power in region 1, certain amount in region 2, as well as battery capacity. And we can look at a variety of other things as well. So how much area have we gone for? What's the kilometers squared we need of concentrating solar power in this region? We can also look at the time series, which we'll look at in a moment after we've added in a new scenario. So this new scenario, which we add in just with a short snippet, brings in this new technology of a combined cycle gas turbine into the mix, loads it into the model. We can optimize that, and then we can look at the capacities afresh, and we can see that there is value to having the combined cycle gas turbine in there. And we could then compare the results between the 2 and say, okay, well, that means we need a lot less concentrated solar power in region 2 if we have combined cycle in region 1. We can also look at how that is in time. So what is the dispatch of technologies at each point in time? This is just over a period of days, and we can see the demand curve. And we can see within that the different technologies meeting demand, or in the case of battery storage, storing in some hours and discharging in other hours. And we could even look at how the CSP stores heat through time and how the battery capacity is stored through time. So this is sort of a very simple representation of how we might want to look at the at a problem, but it's kind of understandably a bit of a toy problem. So it's something where the regions are abstract. There's only a couple of technologies. We're not so sure that the costs really mean much or anything like that. And so for the case of this particular workshop, we're going to be working rather with a representation of a few countries in Europe based on the Euro Calliope version 1. These are given inside a folder on a server that we're going to provide access to so that you can also have a look at it yourselves. So I posted a link a little while ago, and I'm going to post it again for those who just joined, and ask you all to head over to this site, and I'm just going to share what it looks like when you get onto it. So what you'll see is the ability to sign in, but you won't have accounts, so you can sign up. And signing up is very easy. You just put in your name, my name, you put in a password, and then you can create the user. Once you've done that, you just go back into the login, go to my name, and then put in your password. Do remember your password. We can't access your password after the fact, so you can put in something relatively simple, but make sure that it's a password that you will remember. Once you're in, the server will start up, and you will be welcomed with a welcome file, and that's basically it. You can go into here, and there is a link, and you should copy this link and chuck it right back into your server. And that should bring you directly into having all of the data inside your problem, inside your server. So just to repeat, you go to sign up, you then put in your name, create the user, and then you go into the login. So you have to press that login button and then sign in. Click on the welcome.txt, copy this URL, run it, and that will just automatically synchronize your server instance with our GitHub repository of all of the information for today's session. I'm just going to give you all a moment to do that before I move on. Okay, if anyone is having issues with it, do raise your hand and we can discuss it. Whenever you click on a file within the server, what should happen is that it will open the file to one side and your server will always be available as another tab. If you need to get back to it, just type in Calliope workshop.eth.ch, and that will take you directly back to the server for your logged in username. So you'll always be able to get back to the main page if you need to, and new pages should open to the side. All right, so we'll go in. You can follow along with my screen share, or you can, and I would recommend for those of you who have logged in and opened the file structure to follow along yourself on your own server. I apologize if there's not enough screen space available to you to do all at once, but priority should be to you exploring yourself.
You need to zoom in a little bit again, Bryn.
Of course. We're going to go into the Model 2 folder. And Model 2 is a more complex representation of a Calliope model. And rather than just having a single YAML file, you'll see we have multiple. And you can have as many YAML files as you like, and you're going to bring them all together at the end. But here we've got YAML files to represent the different components of the model. And we tend to go for this kind of approach when we're building our models. So we have our text all defined in one location, in one file, our locations in another file, links in another, overrides in another, and then the high level configuration in the final file. And if we look at that file, we can see that what we end up doing is we just end up importing those other YAML files, so that what Calliope sees is one big file with everything in it, but what we can do is have lots of separate files that we just stitch together at the end. The high level information is in here, and we've got our time series data in a folder that we define that's in the main directory. And we're going to use the Gurobi solver, and we're going to minimize monetary costs. So if we look inside some of the files that we've got here, we'll see that it is more complex than the very straightforward example I gave earlier. And I'm not going to ask you to try and understand every single component of this. You can spend some time yourselves at a later point digging into each of these technologies. But suffice to say that it's the same in terms of structure. So you have your technologies, you define a technology, and then within it, you define these essentials, these constraints, and these costs. These costs are more representative of actual expected costs for technologies in the future. And so you have your roof-mounted PV, you have your onshore wind and your offshore wind. We've given units here in comments. So when you use the hash or the pound sign, you can add comments that are just not passed at all. So you can provide information to your future self on what's going on. You can provide information on data sources, on units, or anything else. We've got technologies that you would expect to be modeling with in a decarbonized energy system model. So you've got your renewables, you've got your hydro run-of-river, you've got your hydro reservoir, you've got your biofuels, you've got your pumped hydro, and you've got more novel technologies such as hydrogen storage. You can say, you know, where does it come from, the data, transmission, and as with the previous one, demand. We'll leave the tech groups to one side. For demand, we provide a single file at the technology level. And what this allows us to do is within the CSV file, we can define the location differences of demand. So we can go into our time series data and we have our electricity demand. And a CSV file never looks good when you look at it as a text file, but you have your timestamp, so the day of the year, and you have your countries, and we're going to look at Germany, Italy, and Switzerland. And you have for each of those what the demand will be. And so what Calliope will do is it will load this CSV file, it will know that electricity demand is related to this file, and it will allocate demands to each of the locations based on the column names. As I say, we've got 3 countries. And within these 3 countries, we've got the coordinates of the centroid of those countries. We've got the demand for electricity. We've got onshore wind, PV, offshore, hydro, biofuels, and we've got limits on these. And these limits are related to land area, they're related to offshore area, they're related to the available biofuel crop, maybe related to the actual hydro capacity in those countries at the moment. And so they're broadly speaking based on physical constraints that can be used to understand how viable renewables are for meeting demand in the future. The lat and lon are actually the middle of each of the polygons, but you could choose anywhere. It's partly really just for plotting at a later stage for you, and is only used in very small cases inside the actual model processing. The difference, the other difference between these locations is that Italy and Germany have the option for offshore wind, but perhaps understandably, Switzerland doesn't. So you won't find offshore wind as the list of technologies because it has no coast. So otherwise, they have the same available technologies, but with just different resource availabilities depending on land area and crop availability. We then link those, and linking can be as simple as just saying Germany and Switzerland are connected together, Italy and Switzerland are connected together by AC transmission. We just have to tell the model that those are linked. You could have one location for every single wind turbine that you're interested in, but you might get to a point where your model size is so large that it won't solve. And you've always got this compromise when doing modeling on this. You could also choose to have multiple wind turbine technologies in a single location, and each of those technologies has got a different capacity factor time series associated with it. And that could represent different wind turbines in the same region. We then have our overrides, and we're just going to consider two overrides in this example. The addition of hydrogen. Hydrogen wasn't originally in the technology in the locations provided. And the addition of transmission limits based on ENTSO-E 10-year network development plan. Although I've changed these numbers slightly just to be able to provide some interesting results for this particular test case. You'll see some syntax differences between some of the things we're doing here. For instance, here, we want to provide hydrogen as a technology to these three locations. And we do so quite quickly by just providing them in this comma notation. But we could also do this. And continue that for each of the technologies. But as you see, the file becomes a lot more wordy by doing this. So it can be quite nice to have this comma notation just for locations that share exactly the same information, to do so in a much more concise way. You'll find much more about this in our documentation, which we'll talk about later. That was what I just showed, so we'll just go back and look at the actual notebook. So I would welcome you all to open the Model 2 notebook, because you'll be able to run it yourself and have a look at the results in real time as well. The first thing you have to do is just import the Calliope package. If you've got any experience with Python, you'll know that this is the first step. You then, for Calliope, you need to load the model in, and we only point to the model.yaml, the one that stitches everything together. It loads it in, and now it's pre-processed all of your YAML files and structured the data as in tabular format. So we can look at the inputs, and this is in the form of an X-array data set. You don't need to know the details of that right now. The key element is that they are multi-dimensional arrays. So you've got here your resource, which is, say, the available solar energy, wind energy, or in the negative form, the demand for power. And we can see a relatively complex multi-dimensional array of data. It's nice to have that data stored for you, ready to go for optimizing. It's not necessarily that nice to look at. and to really understand what's going on. So a first step to getting a better picture of the data is to reformat it, and we provide the ability to reformat it. And we're going to reformat the maximum energy capacity here into locations and technologies. And we see that actually we haven't defined information for most of our location technology combinations. So they are NaN, not a number. This is still difficult to tell, which one is Switzerland, which one is wind, it's difficult to visually inspect this information. So rather we use Pandas series quite frequently to look at the data in this format. So now we can see, okay, we've got a maximum energy capacity of roof-mounted PV in Switzerland. And we can look at these inputs both to just sanity check that it's loaded in all the information as we expected, but also if there's any numbers we might want to communicate with other people about our model. And it's restructured it in a way that is more concise than both the YAML file and the X-ray data set, because it's loaded it all in and pre-processed it for us. We can even plot the inputs using the internal plotting functionality. And here we can see the available resource for our variety of technologies. So this is the capacity factor input for our technologies across the year 2016. We're not going to see anything else from the time series perspective because all the other time series are related to outputs. So we haven't solved our model yet, so we don't have any outputs available to us. As you can see in this red bar, we are going to be getting rid of the internal plotting functionality because in our mind, actually a separate module, and we will be bringing it back as a separate module. And we find that when we write papers, when we undertake studies using Calliope, we always just make our own plots for the specific situation. When we want to view data in a particular way, we end up making our own plots for it. And you can do that using matplotlib, one of the Python plotting functions packages. And in this instance, you could look at what is the lifetime of your different technologies in your different locations. You can plot in whatever way you want because you can store the data and load it back into whatever program you're interested in as well. We then want to run the model. The interesting parts are in actually solving it. So you can just model.run, go, let it do its thing. You can run this yourself in the notebook that you've got open, if you've got it open. And then we get a solution. The solution to this model is going to come in the matter of tens of seconds. A model that is of a larger size might take minutes to hours to run. Once we've got the solution, we can plot the time series. And here we see a much more information available to us compared to plotting the time series as an input. We have the input that we looked at earlier. This was what I showed you earlier, the available resource. But now we have the output in terms of the flow of electricity. And so we can see things like in the summer, much greater PV production, in the winter, much greater wind production, both onshore and offshore, but also much greater use of storage facilities as well. Using this plotly functionality, you can also tick these values on the side to zoom in on certain technologies if we're interested in them. So we could zoom in on roof-mounted PV, zoom in on a particular month of interest and have a look at what the results look like there. And you can do all of that yourselves as well in the notebooks that you have open and perhaps have also run yourselves already. We might also want to see what some of the results look like just in terms of hard numbers. And so we could look at energy cap. So that is the capacity, discharge capacity of our technologies. And we take that to a Pandas series, get rid of any not a numbers, round the values to 2 decimal places. And then we have some results that we can look at. So what is the biofuel capacity? We can see that Switzerland has got a much lower biofuel capacity than Germany does. I mean, in fact, Germany's got much higher than everywhere else. And roof-mounted PV is predominantly in Italy. and things like that. So we start to get a picture of what our least cost energy system is. We can then bring in scenarios, as I did with the test model. So we bring in the transmission limits and we run that. And bringing in the transmission limits causes a problem for our model, because what we had before was a large amount of production of PV in Italy, which would probably be transmitted to neighboring countries. And instead we get this. Our problem is infeasible or unbounded. It means that with all of the constraints we're putting in, it's impossible to meet demand with supply. And this is because of our transmission limits causing that problem. So we'll try here adding in another override. And you can add in as many overrides as you like at once by just using this comma notation. And we can run it now with hydrogen storage as a seasonal storage device. We've loaded in the inputs. We don't have the outputs yet. Let's see what those might be. So we run that. I would say for those who haven't used Jupyter Notebooks before, when you want to run a cell, you use the Shift or Alt Enter. And then when you want to enter a cell, you just use Enter. So then we've got the results and we can plot the time series. This looks different to what it looked like before. Let's just have a quick run back to where we were before. We'll put this all back on. And we've got this small amount of hydro use in the winter, large wind and large PV in the summer. We go back to this new one and we can see a much larger wind production throughout the year and a much generally lower difference in the PV production and a large use of our hydrogen storage. And we can look at what that storage looks like by going here, and what you see in the bars here, in the lines, is how filled the overall storage reservoirs are. And we can see that both for hydro and for hydrogen, that they are acting as a seasonal storage device, building up the storage throughout the summer and the spring and discharging it throughout the winter. And we can see that here with this line here. I'm sorry about the large banners that come up at the side that make it difficult, but then we can see that as the line here as well for hydrogen. Pumped hydro is acting more on a daily level, and we can see that line lower down here, that it's fluctuating much more wildly throughout the year in terms of its overall capacity. So I've just been asked in the chat about where this is hosted, and yes, it's on a Jupyter Hub server. Stefan's just answered. Stefan, if you want to just provide the link as well, in case that was lost by people joining late. We can also look at the capacities, and we can see here the roof-mounted capacity, the offshore wind capacity in these different locations. And we can also look at, say, the amount of area being used by these different technologies in terms of kilometers squared. We might want to compare these different outputs, and it's not necessarily straightforward to do that at the moment, but what we're going to do as a quick fix is to load them in as pandas series. And again, I'm not going to ask you to understand all of this if you're not familiar with Python programming or pandas or X-ray packages. But safe to say, I'm going to compare the costs here, and I'm going to compare the capacities between the two. So we run this, we can look at the costs. The first model run had this. It's in million euros. It's a bit of an abstract value. It's just a very large number. Yeah, I'm pretty sure it's a million. And the second model run is slightly cheaper. That's the main thing. It's usually good to think of these things in terms of their relative values rather than absolute. And we can see that there is a slight difference in cost between the two. So you add in the ability to use hydrogen storage. It purchases a certain amount of that hydrogen storage, and it makes the overall system cost lower. And then you can look at the results yourself if you wanted to, comparing between the two in terms of the capacities. Been asked about how you can handle this infeasibility. Rather than just getting this, you might want to know where the infeasibility is happening so you can debug your problem. And you can do that relatively easily by adding in an override. And this gives us a chance to just look at one of the additional functionalities that we have, which is to provide effectively a YAML file, but directly in the instance that we're running in Python interactively. And we can ask it to ensure feasibility. So we can run that. I'm just going to call this a different one now, very originally named. This will run and it will solve. So unlike the previous case, it's solved. So then we can look at where the infeasibility turned up. And we can see that I need to run it. So we can see that it will run, it should run, all being well. So we've loaded it, we've added this additional thing, and this is just using the same YAML format. So run.ensure feasibility, it's a configuration option you could even have in your YAML file directly. And we'll see that it has optimized. It has a solution. And here we have an additional technology called unmet electricity demand. And we could zoom in on this if we wanted to and see when that is worst. And we can see it's particularly bad at certain points in the winter. And that allows us to understand where the infeasibility is turning up. A very handy debugging option. Great, so that is this notebook, and I would ask you all now to just, if you haven't already, open up that notebook in the server yourselves and just run through it. Maybe look at the plots yourselves, and we'll just give you 5 minutes to do that before giving you a problem to add to this particular model to make it more complex and to add additional insight. So just give you a few minutes now. Feel free to ask questions directly in the chat, or just raise your hand and you can chat in the session yourselves. We're only 18 people, so do feel free to raise your voice as well if you've got any questions. So this is the debugging option, and I could also have put this directly in the YAML file so that every time I run my model, it's always got this ensure feasibility component included in it. To show that, if I were to go to this YAML file, we see this run here, which is the same as the run in here. And we can then just say, add in an initial option, true. And that will mean that every time we load our model, it will catch this infeasibility. We tend to advise that if you know that your model will be feasible, so you've got to the stage where you won't have infeasibilities, not to use this option, because it can have an impact on the time it takes to reach the solution. It makes the model slightly more complex to have this ensure feasibility component in it. So the usual approach would be to not have it. If your model is infeasible, put it back in, rerun it, solve the infeasibility, and then remove this option afterwards. You can also add in additional information if you wanted to by telling Calliope to be more verbose with its information that it provides you. This can be overloading. So it's sometimes not that useful, but we can set this value. And then when we run the model, we'll just reload it. We can see that it brings in it gives us a bunch of information. And then we can rerun it, and we can see that it's creating certain constraints. It tells us how long it's taken to do those, sending it to the solver, and the solver will run it, and it will tell you a load of information about how close it is to getting to the solution. It will tell you it's solved, and then Calliope will tell you it's post-processing. You can do all of this without needing to know Python at all. This is a key component of what we do, is to be able to do that. And in fact, we could, in the terminal, Calliope is an option available to us. It's a command line interface option. So you can see that by running Calliope in the command line, we can run a model as well. We could run, this is something that I don't do very often and probably then shouldn't do in front of an audience, but we could see whether there's any information about that. Yeah, so we've got, and then we need to point to the model file. So we'll go into there, we'll go to the model 2, and here's a model.yaml. And we probably want to save the results, and I think it's like this. And then we can say that we put it into there as a netcdf file. So it's not that. So what is it? Save file. Does anyone remember? Maybe I can look at the documentation. So we can look at the Calliope documentation, and it will tell us how we would run a model, and it's save_netcdf. So I can go back and I can see, oh, what did I do wrong? I did save dash, so I can do save underscore. And now it will run the model purely in the command line. We don't have to touch Python. And we can then see the model optimizing, gets a result, saves it to a netcdf file, and then it's completed. And now a netcdf file is useful for use for processing in Python, but also I believe in R. It is also possible to save as CSV files, which you might find if you don't want to have to touch it at all, is the better option. And so you can do this. It will rerun the model. It's going to solve it, and it's going to save all our outputs as CSV files that we can process later if we want to. So I can go here and I can look at model outputs. And here we've got a lot of CSV files because there's just a lot of data. But let's look at a result. So results energy cap. And here we've got, as a CSV file, for each location, what is the capacity of each technology? Saved as a CSV file for us to process in whichever way we like. We could open it in Excel and process it in there if we wanted to. So that allows us to avoid Python entirely if we wanted to, but Jupyter Notebooks are a nice little way to get into using Python and using Calliope in an interactive manner that allows us to look at the data as we're working on the model. Okay, so we're going to now put you into breakout rooms where you're going to work in small teams on introducing a couple of new components to the model. As I was saying yesterday in the sector coupling session, coupling multiple sectors into our modeling is very important to understanding the decarbonisation of our energy systems. And so I've created a problem where you need to add in heat demand to the problem and technologies to meet heat demand. You'll find it in Model 3, the definition of the problem, the notebook Model 3. And what you'll see is that there is a CSV file of heat demand available in a different folder. You'll need to move that into the right place to be useful. And then you also have characteristics of two different technologies, a gas boiler and a heat pump. The main values are here in this row, the value row, value column, sorry. In terms of efficiencies and lifetime and costs, and for gas boiler, CO2 emissions. And the heat pump has also got these, but it also has location-specific efficiencies based on the differences in average air temperatures. You can add the boiler as a supply technology, and you can find a link here to our documentation on defining supply technologies, and the heat pump as a conversion. Similarly, there is a link. You can add these technologies in as individual components. Maybe you want to add them in as an override to the basic model that's already there, so that it loads those in as a scenario when you want to add them in. And then there are a variety of additional problems that you can look at if this is all too straightforward for you. It's difficult to tell in advance exactly where people are at in terms of their ability with Calliope. So there are some additional elements. What was asked in the chat was about units, and it's important to be careful about units because you have to keep track of them yourself. And the units of this model here are in gigawatts or gigawatt hours for power and energy. And sorry, €1,000,000 per gigawatt or gigawatt hour for costs. So those are the values you're going to need to ensure that your inputs are based on when you put them into your YAML file. I'm now going to just stop sharing. I'm going to give you all co-host rights. You're all going to become co-hosts for the next 30 minutes. And that will allow you to share your screens within your breakout rooms if you want to share information with each other. So we'll do that. And if you have any questions when you're in your breakout rooms, there should be the option to request help. And myself or Stefan or Francesco or Tim will drop by your room in order to be able to provide you some help. I think actually I might be able to allow participants to share screens, so that should actually do it as well. So I'm withdrawing your co-host permissions because you should be able to share your screens with this new functionality. Great, so there we go, that's done. And then we're going to put you into breakout rooms. Of 2 to 3 people. Actually, no, 3 to 4, because some of them will be us. Good. We'll just okay. So we're just going to open all those rooms, and I'll just say to Francesco and Tim, don't join your rooms. You can ignore that, and everyone else, head into your rooms, open up Model 3 notebook, and see where you can get to. We'll drop by to see what issues you may or may not have. We have, okay, Miguel's joined. Daniel seems to not be there, so I'm going to move Mahendra to
room 3, maybe.
And I will ask Daniel to join room 4 if he does turn up. Great.
Oh, okay. Yeah. So he did show up, or at least click on the button to get to Zoom.
Mm-hmm. Cool. So that's 3 people in each room. That's good enough.
Cool. So far, so good. Well done. I think this is going to be tricky because they have less than half an hour now.
Yeah. Yeah. I think the likelihood is that they won't manage to do it. But even if they just add in a single technology, that will be better than nothing. And I will, well, yeah, I will provide the solutions as an additional file in the GitHub repository after this. I don't know whether it makes sense for us to wait here or to actively just go into the rooms and spend time with them. Maybe we give them some time.
I think we should give them some time and then go there. Mm-hmm. Since we now have just three rooms, we have more than enough manpower.
Yeah. So Tim or Francesco,
one of us can even head off.
Yeah, if you want to head away, you can.
All right. Yeah, actually, I think you have just 2 rooms, don't you? Because it seems like room 2. I know room
no,
1,
yeah, 3, and 4.
Yeah, it's a bit mess. Okay. I see it. Yeah, okay.
Yeah, because you can't, once you've automatically assigned someone to a room, you can't unassign them.
Yeah.
Yeah, I think the units is a good thing that we need to consider how to deal with. At least being able to have some metadata with units that passes all the way through to the results file.
Yeah. Agreed.
And I noticed, and this has always been a perpetual problem, is the idea of how you deal with transmission capacities in terms of plotting them and viewing what those values are.
Yeah, I think
the solution to that.
I think one nice add-on and easy add-on to the plotting functionality would be to allow to subset 4 locations or to plot 2 locations at the same time.
Oh, you can.
Can you? Because I've never managed to.
You can subset individual, like you can slice the data any way you want, I think, but it will always aggregate then over what's left.
Mm-hmm.
So if you slice on 2 locations, it will then provide the data for 2 locations, but aggregated.
Right.
You can't have 2 locations side by side. So. At least that you can certainly subset. I wonder how well it would work.
I'm not sure if Tim is even listening. He's just sort of staring at the screen and doing something different. No, he is. Yeah, it's a good way to check name check someone and see whether their facial expression changes.
But that means there is only sound coming, right? It doesn't mean that people are listening, because as soon as you say the name, they will start.
Yeah. But at least you have to. I mean, you could also have muted the sound and just pretend.
I'm not that far, but I'm almost as far, I have to admit.
That's fine. I mean, you don't have.
But yeah, if you want to leave, I think, then it's fine.
I can also stay the way I stood for the last hour and do other things next to it.
Deeply interested in everything I had to say.
Sorry, I think it's not the first time I heard these things.
No, it's not. Yeah, it's definitely the case.
How much time do we need to close up? Do you need to say anything? Do we need, I mean,
ideally we would, I think it is possible to wait, what's after this session?
No, because 10:30 is the next, is the next session.
And
so
they
actually
need room one to, yeah, I think it's actually quite tight, isn't it?
Oh, do they need? No, I don't think
No,
so,
they
because
don't
it's a
need
plenary
room one.
session. So they don't
Yeah.
need this one, but they want people to go to the plenary. Although, I mean, it's the first 30 minutes is this like wrap up and welcome and stuff, which.
You're being recorded, careful.
Damn it, yeah. See,
Oh,
this
are
is why I
we?
don't
Okay,
like recordings.
Okay.
Which is important for everyone to attend. That's what I want.
Yeah. I think it is useful for everyone to go to, but they'll have like a 5-minute sort of ramp up to anything useful anyway as people trickle in. So I think we maximize anyone who's interested in Calliope, their time here, and then go from there.
I guess we're not allowed to keep this open and tell people they can stay on this.
Hi, Danielle and Christina. We've got a lot of sudden interest. Are you both there? Are you able to say something? We have people at the moment. Yeah, we have people at the moment in breakout rooms working on the model. Stefan, if you could just repost that text about the links. There's some instructions to gain access to the online server to work with Calliope that will come up in the chat. You can head on there, and I would highly recommend you to then go into Model 2 and look at the files there, and also to load the Model 2 Jupyter Notebook. And you'll find, I've already gone through it, but you'll still find a commented notebook that you can go through to understand what's going on. Christina, the same applies. And what I will do is I'm going to put the two of you in a breakout room, and then you can ask each other questions if you like, and you can also request information from us if you want to understand what's going on. But obviously, the main information has already been passed over, so you won't get most of that. So let me just assign you into a room. And do request information from us if you want, or request help, and we'll jump in and provide you with that help. I guess this is the problem with doing these things online, is the ability to drop in and out of sessions at any time, and almost having to be ready for that moment in a way that you wouldn't be in an interactive session in person. Okay, maybe Christina's by themselves in that, so I might just move them to another room and they can just jump into the fire. Let's move them into the one with the other Christina to make it even more complex.
Okay, I think we should probably I think you can only do that as host, Bryn, send and announce, or no? No, anyone can do that. Any host can do that, broadcast message to all. When do we want to close the room so they have an idea? So that's always annoying if you're in a breakout room and then suddenly they just close.
So we say 25 past?
Yeah. Or should we even say 20 past? No, they didn't really have any questions, it seemed. Or we don't really have enough time to go into depth with questions anyway, so might as well.
Yeah, and we can also just jump into the breakout rooms now and.
Yeah, I think we should do that.
Um,
Okay. I see Francesco's I'm not actually assigned to anyone, but I can go any room, but I can go to room 3, which has nobody assigned.
Cool. Yeah. Francesco, you head to room 4. I'll head to.
Yeah.
Actually, Tim, do you want to head to room 1, and then I'll just handle people if they come in randomly.
Okay. See you.
Thank you. All good.
Yeah, they're on a good track, I would say. So I left them themselves.
Great. It's always difficult to know where to start people off. But
yeah, I mean, yeah, I think I mean, they won't have enough time. That's for sure. When did you want to close? In 5 minutes? 6 minutes?
8 minutes.
8 minutes. Yeah.
But yeah, they won't have enough time. That's true.
Is there any option they can doing this?
Well, the server will remain open.
Yeah.
So they can continue doing that, and I have the solutions already in a file, and I will put that on the GitHub repository, and then people can synchronize that using the synchronizing link again. And so they can see at least the solutions afterwards if they want to.
Good.
Okay, sorry for dragging you all away from your fun, but the plenary is going to be starting in a few minutes, so we have to wrap up. I'll give the floor to Stefan in a moment to do a few minutes of wrap up, but just to say that you probably didn't reach the point of being able to have what you wanted in your model, and you can still work on this, but also I'm going to be putting a sort of a solution to this, so how I would write it to solve this problem, onto the GitHub repository. And you can rerun that link I sent you, this tiny URL with EMP-E Calliope 2021, and that will bring it into your Jupyter Hub server instance, and you'll be able to have access to it yourself as a solution. So I recommend giving it a go today or tomorrow to try and finish it, and then accessing that if you want to. I'll put it up later today. So you have the chance. Stefan, over to you.
Sorry, thanks, Bryn. I'm struggling with a tiny laptop screen and a gazillion open windows right now. So yeah, so this was a very quick introduction to Calliope. And we hope that you got a sense of how Calliope works and how it's designed. And the key thing really is that it provides building blocks for you to build the model. So you will start with defining a bunch of technologies, some storage, supply, demand technologies. You encapsulate those in locations. You define how these locations can be linked together. And ultimately, you define the sort of all-encompassing model and run configuration, model-wide constraints, scenarios, overrides, and so on. And all of that you can do in a simple text-based format, the YAML files that Bryn has been showing us all morning. And of course, we looked at really simple examples now, but you can take these building blocks and you can go to a massive amount of complexity. You can build very large and complex models with this. And here just two examples from our own work from published last year of what you can do starting with these building blocks to build very large models. Now, what we also like to highlight is that one of the design goals of Calliope really was to build problem-specific models. To sort of start with these building blocks and put them together to solve a particular research question or a particular problem that you have. And to do that in a way that lets the underlying model remain human readable. And why is that important? We think it's important because models that are used to make decisions, policy decisions or planning decisions should be transparent and they should be understandable. So if you think of a model, an energy system model, as something that encapsulates a research question or a problem which lead to certain assumptions being made and data being gathered, and then a model formulation that takes in these assumptions and data, and all of that constitutes the model together, then it's really important that all of these aspects are actually there for someone who uses this model, for someone to understand what is happening inside. And so the idea with Calliope is that it helps you to do these things, and it helps you to take these building blocks and to really clearly formulate your assumptions and your data based on the research question that you have. And to do that every time again when you come with a new question, to start with the building blocks and build a new model. So where to go next? We mentioned it already in the chat that this server will remain open until the end of the week. I guess we didn't really define what that means exactly. Let's say maybe Sunday midnight or something like that. We can keep it running indefinitely, but for those of you who have a user account on it now, you can continue running models on there and playing around. The documentation is here. It's very extensive. Please make use of it, and also feel free to give us feedback on the documentation if anything is unclear or if you think something could be more clearly explained. And the code, including the issue tracker for bug reports, is here on GitHub. And finally, also to flag this EuroCalliope thing, which you've been working with a very small extract of a EuroCalliope model right now. And that lives here on EuroCalliope.readthedocs.io. And the key thing there is that it's a set of data and workflows to help you build European models with Calliope. I think that about sums it up. Bryn, am I missing anything? We're already 2 minutes over time, so we're supposed. We're supposed to shepherd you off to the next session, but maybe we can take a couple more minutes to finish off here.
Exactly. Anyone who wants to head off to the plenary right away, do so. Anyone who's got any burning questions, thoughts, feedback, please stay in the chat, stay in the conversation. We'll stick around and have a conversation for a few more minutes.
Yeah, so thanks a lot, Bryn, for this great tutorial, and thanks all for joining. Like Bryn said, if you have any questions.
Stefan, I would have one question if you have time still. Yesterday we heard a lot about a lot of different models, and in terms of performance and flexibility, how does Calliope compare to, I don't know, a PyPSA and the other capacity expansion models that we heard about?
I would say it's got comparable performance. So how long it takes to reach the solution of a model is comparable. If you get to a large enough model size, they all need to have sort of a high performance computing cluster involved in the process. In terms of usability, the PyPSA models are very good for working with the models they've created. So say the European model, and tweaking certain values in that in terms of constraints you want to apply or policy measures you want to apply to that. Whereas Calliope is particularly good for just completely reimagining a system and writing it from scratch yourself, as well as taking models that already exist and adding on a variety of scenarios that maybe even the designers, so ourselves, have never thought about doing before. So in terms of flexibility, I say we do pretty well on flexibility, but and then a comparable on performance.
Thanks, Bryn. Thanks.
Maybe just to add, I mean, ultimately, all these models end up being large linear or mixed integer optimization problems. So ultimately, the performance is bounded by the third-party solvers that everyone uses. Here we use Groby, which is most commonly used because it's the most performant, but there's kind of this external constraint that ultimately hits all of these models exactly the same way.
Right. Thank you.
Looks like
Hi, I've got one quick question, if that's okay. We run on the AWS cloud, so I guess at the flip of a switch, we can switch to whatever types of instances they offer. Do you have any tips for recommended configurations there?
We don't use AWS, so I don't think we can comment on AWS specifically. But I think the key thing with, again, coming back to ultimately the biggest computational part is of solving this model is in the third-party solver that actually solves the optimization problem. And the main algorithm is actually not parallelizable, so having lots of cores doesn't necessarily help. Having one core or a few cores with higher performance is preferable, and then usually memory is the limit. So some high memory lower core number machine is probably best. I see others nodding, so.
Okay, good to know. Thank you.
Our general experience.
And thanks very much for the session. Very useful.
Thanks for staying up for it or waking up for it.
Thanks very much.
Cool. Well, then I guess we'll leave you all to head off to the plenary and close this session, this Zoom call now. And as I say, you can carry on using the Jupyter Hub for the next few days. I think I'll probably close it on Monday. And I will post on the GitHub repository the sort of solutions to Model 3, and you can synchronize those directly into your Jupyter Hub by rerunning that link, that tiny URL link to get it. I'll do that today, so tomorrow you can definitely get access to them. So thanks again. Stefan, just put that tiny URL in, so do save that before you leave. And yeah, hopefully see you all on various Calliope channels in the future.